Far out in the cold expanse of our solar system, hidden beneath a shell of ice that glistens like a cosmic jewel, lies one of the most tantalizing mysteries humanity has ever pursued. Jupiter's moon, Europa, a world of breathtaking contradictions frozen on the surface, yet potentially warm and alive below, holds secrets that could redefine our understanding of life itself. For centuries, we've gazed at the stars and wondered if we are alone. Now we stand on the verge of an answer, and it's waiting for us not in some distant galaxy, but right here in our own celestial backyard. Imagine for a moment a vast ocean locked away beneath miles of ice, warmed by the gravitational tug of a giant planet, swirling with currents and chemistry that might just be nurturing life forms unlike anything we've ever known. Those mysterious cracks weaving across Europa's surface aren't just geological features, they're potential doorways, nature's own invitations to explore what lies beneath. This isn't science fiction, it's the cutting edge of exploration where robotic missions are being designed to delve into these very fractures, seeking answers to questions that have haunted us since the dawn of time. What if the first alien life we discover isn't on a far-off exoplanet, but right here, next door? Join me as we embark on a journey to unravel one of astronomy's greatest enigmas, the possibility of life on Europa. We'll explore the science behind those icy cracks, the technology that might help us peer into hidden oceans, and the profound implications of what finding life would mean for all of us. This is more than a story about space. It's about human curiosity, our relentless drive to explore, and the awe-inspiring reality that we may be closer than ever to unlocking the universe's most guarded secrets. Strap in, we're about to dive deep into the unknown. So what exactly makes this distant moon so captivating to astronomers and dreamers alike? Europa is one of the largest of Jupiter's 92 known moons, a world slightly smaller than our own, yet it presents a landscape utterly alien and starkly beautiful. Unlike our pockmarked moon or the rocky plains of Mars, Europa's surface is a breathtakingly smooth expanse of water ice, crisscrossed by dark, enigmatic fractures that stretch for thousands of miles. This icy shell reflects sunlight with such efficiency that it ranks as one of the most reflective objects in our entire solar system, a brilliant white cue ball floating in the eternal night of space. But its dazzling exterior is merely the cover to a far more incredible story. The true magic of Europa, the reason it has captured our collective imagination, lies hidden from view, sealed away beneath that frozen crust. For decades, evidence from spacecraft like Voyager and Galileo has been piecing together a compelling case. Scientists are now overwhelmingly convinced that Europa harbors a secret ocean, a vast global body of liquid water buried under an ice shell that might be dozens of miles thick. Think about the scale of that for a moment. This isn't a small lake or a buried reservoir. Initial estimates suggest this subsurface sea could contain more than twice the volume of all the water in Earth's oceans combined. It is a world-spanning, dark and profound abyss. This leads to the most critical ingredient for life as we understand it, liquid water. And Europa's ocean isn't just a frozen relic. It's almost certainly kept in a liquid state by the incredible forces acting upon this small moon. As Europa orbits its immense parent planet Jupiter, the moon is squeezed and stretched by the gas giant's tremendous gravitational pull. This constant, rhythmic flexing generates immense internal heat through a process called tidal heating, effectively preventing the water from freezing solid. This same process is believed to power hydrothermal vents on the ocean floor, much like those found in the deepest trenches of Earth's oceans. On our planet, these vents are oases of life, thriving with bizarre organisms that draw energy not from the sun, but from the chemistry of the superheated water and minerals gushing from the Earth's interior. This parallel makes the possibility that Europa could host similar ecosystems not just a wild speculation, but a solid scientific hypothesis. It's this powerful combination, a huge liquid water ocean, a likely source of energy, and the right chemical building blocks, that elevates Europa from being just another moon to our single most promising candidate for finding extraterrestrial life within our own solar system. The story of how we came to know about this hidden ocean is a brilliant detective story written not with words, but with data spanning decades and delivered by robotic emissaries traveling billions of miles. Our first good look at Europa came from the twin Voyager probes in the late 1970s. As they raced past the Jovian system, their cameras sent back grainy but revolutionary images. Scientists expected to see a dead, cratered world like our own moon. Instead, they saw a surprisingly smooth, bright surface scarred by a bizarre network of dark, crisscrossing lines. These features didn't look like impact craters, they looked like cracks. It was the first hint that Europa was not a static ball of ice, but a geologically active world. But the real breakthrough, the evidence that turned an intriguing hypothesis into a near certainty, came from the Galileo mission. This dedicated spacecraft arrived at Jupiter in 1995 and spent 8 years conducting a detailed tour of the planet and its moons. Galileo's instruments didn't just take pictures, they took the moon's vital signs. One key piece of evidence came from studying the planet's magnetic field. As Europa moves through Jupiter's immensely powerful magnetic field, it generates a secondary or induced magnetic field. The only plausible explanation for this is a global layer of a highly electrically conductive fluid beneath the surface. And on a cold, icy world, the best candidate for that fluid is a salty, liquid water ocean. Galileo's cameras provided the visual proof to match the magnetic clues. They revealed the surface in stunning detail, showing us that those dark cracks are actually complex bands where the ice crust has fractured, separated, and been filled in with newer, darker material from below. We see regions of chaotic terrain, great chunks of ice that have broken apart like puzzle pieces and then frozen into new, jumbled arrangements, suggesting that slush or even liquid water had welled up from below before refreezing. The surface geology painted a clear picture of a world where the icy shell is geologically young and constantly being resurfaced, effectively erasing the evidence of ancient impacts. This ongoing activity requires a powerful internal heat source and a liquid layer beneath to allow for such mobility. Piecing all this data together, scientists reached a monumental conclusion. Europa isn't just harboring a few pockets of water. It possesses a global ocean encased in an ice shell estimated to be 15 to 25 kilometers thick. The volume of this ocean is staggering. While Europa itself is only about a quarter the diameter of Earth, its ocean is thought to be immensely deep, perhaps 60 to 150 kilometers deep. This vast volume means that, unbelievably, Europa likely holds more than twice the amount of liquid water found in all of Earth's oceans, rivers, and lakes combined. This realization fundamentally changed our perspective on the solar system. The essential ingredient for life isn't rare or unique to our warm, rocky world. It exists in incredible abundance, sloshing in the darkness around a giant planet, waiting for us to find a way in. This global ocean, however, is sealed away beneath an incredibly formidable barrier, a shell of water ice that forms the moon's visible surface. This isn't a simple, static layer of frost. It's a complex, dynamic, and geological active crust that plays a completely contradictory role in the search for life. Scientists estimate this icy shell is between 10 to 30 kilometers thick. To put that immense scale into perspective, if you were to stand on the surface, the ocean below would be buried under a ceiling of ice deeper than the Mariana Trench is deep. This shell is Europa's ultimate protector and its most significant challenge. Its primary function is that of a planetary shield. The surface of Europa is bombarded by intense radiation from Jupiter's powerful magnetic field, a constant storm of high-energy particles that would instantly sterilize any life unprotected. The ice cap acts as a natural barrier, absorbing this deadly radiation and creating a safe, dark, and insulated environment for the ocean below. It maintains the ocean's liquid state by preventing heat from escaping into the frigid vacuum of space, effectively acting as a giant thermos lid for a world-spanning sea. Without this protective blanket, the prospects for life would be vastly diminished. Yet this same shield is also the locked door we must find a way to open. A shell 30 kilometers thick is an almost unimaginable obstacle for any exploration. But here's where Europa's nature turns obstacle into opportunity. This ice isn't a single, solid block. Data tells us it's geologically active, likely divided into layers. The top is brittle and cold, fracturing into the immense cracks and ridges we see. But deeper down, the pressure and heat from below may warm the ice, creating a warmer, softer, even slushy layer that behaves more like the tectonic plates on Earth. This constant activity means the shell is not a permanent barrier. It is constantly being recycled, with new material welling up from below and old material being pushed aside. This dynamism is written across the surface in the form of those vast, dark bands and regions of chaos terrain. Those cracks are essentially the planet's stretch marks, evidence of the shell being stretched and pulled apart by the gravitational tides. In some places, the crust has completely fractured, allowing water from the subsurface ocean or from warmer layers within the ice itself to seep up and out, where it instantly freezes on the bitterly cold surface. This process might even be cycling nutrients and energy from the surface down into the ocean, as darker, irradiated material from the top gets pulled back down through the churning ice. This constant geological recycling could be the very engine that makes Europa habitable, mixing the essential ingredients for life between the protective ocean and the chemically rich surface. So while the ice shell is a formidable physical barrier to us for any potential life in the ocean below, it is a vital, active, and life-sustaining system. The relentless, invisible hand behind this incredible geological activity is the overwhelming gravitational force of Jupiter itself. As Europa travels along its slightly elliptical orbit, its distance from the giant planet is constantly changing. Jupiter's gravity pulls harder on the Moon when it's closer and relaxes its grip slightly when it's farther away. This rhythmic squeezing and stretching doesn't just flex the Moon by tens of meters with each orbit. It generates immense internal friction and heat through a process called tidal heating. This is the engine that powers everything. It keeps the subsurface ocean from freezing into a solid block of ice, and it supplies the energy that constantly reshapes and fractures the icy crust above. Without this perpetual internal warmth, Europa would be a geologically dead, frozen world. This constant flexing expresses itself directly on the surface, creating the most defining feature of this alien moon, its vast global network of cracks, ridges, and bands. These are not like the simple cracks in a frozen puddle on Earth. They are tectonic features on a planetary scale, some stretching for thousands of kilometers across the landscape. The process is thought to work in a way that has fascinating parallels to and key differences from the plate tectonics that shape our own planet. On Earth, our rocky crust is broken into plates that float on a molten mantle, sliding past, colliding with, and diving beneath one another. Europa's icy shell seems to behave in a similarly mobile way, but instead of rock, it's a cap of water ice. As the Moon is stretched by Jupiter's tides, the brittle upper ice fractures. In some regions, these fractures open up into gaping fissures. Scientists believe that warmer, softer ice or even liquid water from the slushy layer below can then well up from the interior to fill these cracks. When this material reaches the brutally cold and airless surface, it instantly freezes, creating the dark, smooth bands we observe crisscrossing the terrain. In other areas, the crust isn't pulling apart but is instead being compressed, forcing slabs of ice to slide over or under one another, building up complex ridges that can run for hundreds of miles. This creates a surface that is constantly being recycled and renewed, with old radiation-blasted ice being pushed down and buried, while fresh, new ice is being emplaced on the surface. This cyclical process is absolutely crucial because it might be the mechanism that transports oxidants and other chemicals from the surface down into the ocean below, potentially providing a vital food source for any life forms that might exist in the darkness. The most striking evidence for this active resurfacing can be seen in regions known as chaos terrain. These are vast, broken areas where the surface ice appears to have shattered like a pane of glass, with large icebergs and blocks that have been tilted, rotated, and then refrozen into a new, jumbled matrix. It looks as though a colossal upheaval occurred, perhaps because a large body of warmer water rose close to the surface, melting and breaking the ice from below before everything refroze. These chaotic regions are a clear testament to the powerful and dynamic forces operating within Europa's ice shell, suggesting that the boundary between the solid crust and the liquid ocean might be far more complex and interactive than a simple, sharp line. It paints a picture of a world that is not just a frozen ball with a hidden sea, but a geologically vibrant and ever-changing environment where the door to the ocean below might not be as permanently locked as we once thought. Among the most compelling and visually striking evidence of this dynamic activity are the regions scientists have fittingly named chaos terrain. These areas look nothing like the long, linear ridges and bands found elsewhere on Europa. Instead, they resemble a colossal pane of ice that has been violently shattered by some immense force from below, leaving behind a bewildering jumble of icebergs, blocks, and debris, all frozen into a new, grotesque matrix. The most famous example, Connemara Chaos, was imaged in stunning detail by the Galileo spacecraft. It shows a vast, fractured expanse where house-sized and even mountain-sized blocks of ice appear to have been tilted, rotated, and displaced before being re-anchored in a slushy, refrozen base. It looks less like a landscape and more like a puzzle that was broken apart and hastily put back together by a giant hand. The existence of such terrain points to an incredibly powerful and localized process operating within or beneath the ice shell. The leading theory suggests that these chaotic regions are essentially the scars left behind by significant thermal upheavals. Imagine a large body of relatively warm ice, or perhaps even a pocket of liquid water, rising up from the deeper, warmer layers of the crust due to convective currents, much like a blob of warm wax rising in a lava lamp. As this buoyant mass ascends, it carries heat with it, partially melting the colder, brittle ice above. This melting destabilizes the entire region, causing the surface to founder, break apart, and collapse. The large, solid blocks of the old surface float and tumble in the temporary slushy meltwater before the entire system eventually cools and refreezes solid, locking the chaos in place for eternity. This process is absolutely critical in the context of the search for life, because it suggests a direct two-way exchange between the surface and the hidden ocean. Chaos terrain acts as a natural elevator, potentially transporting material between the two realms. Chemicals from the surface, which have been processed by Jupiter's intense radiation, could be carried down into the ocean, providing potential metabolic energy for life. Conversely, material from the ocean, including just possibly biomarkers or even dormant microorganisms, could be brought up much closer to the surface, frozen in place within this chaotic ice, waiting for a future lander to discover it. These regions, therefore, are not just geological curiosities. They are potentially the most promising places on Europa to look for signs of life, as they may offer us a relatively accessible sample of what lies in the abyss below without requiring us to drill through miles of solid ice. While the chaotic terrains are dramatic evidence of Europa's inner workings, the Moon's surface is dominated by a far more widespread and subtly telling feature: vast networks of double ridges. These formations are literally everywhere you look, crisscrossing the landscape like frozen railway tracks or the stitches on a cosmic baseball. A double ridge is exactly what it sounds like. Two long, parallel ridges running side by side with a shallow valley running down the center between them. They can stretch for hundreds of miles, and they are the most common topographic feature on the entire Moon, suggesting that the process that forms them is fundamental to how Europa's icy shell behaves. For a long time, how these ubiquitous structures were created remained one of Europa's most persistent puzzles. But a compelling theory has emerged, one that not only explains their formation, but also provides a thrilling clue about what might lie just beneath our feet. This is known as the shear heating model, and it paints a picture of a far more dynamic and accessible subsurface than we ever imagined. The process begins with those ever-present tidal forces from Jupiter. As the Moon flexes, it doesn't just crack the ice, it also causes immense slabs of the crust to grind against each other along fault lines. This friction generates significant heat through a process called shear heating. Think of it like rubbing your hands together very fast on a cold day. The friction makes them warm. Now, imagine that happening on a planetary scale. As two blocks of ice slide past one another, the friction at their boundary can generate enough heat to actually melt the ice locally, creating a pocket of liquid water or very warm slush right within the solid ice shell. This suddenly liquefied material, now trapped under pressure, wants to escape. It forces its way upward through the weakened zone between the two grinding slabs. As this watery mixture erupts onto the bitterly cold, airless surface, it instantly freezes, depositing material along both sides of the fracture. Over countless cycles of this grinding, heating, and erupting process, the frozen deposits build up, eventually forming the two distinct, parallel ridges we see today, with the original crack still visible as the central trough. The profound implication of this model is that it suggests the presence of a shallow, liquid water table. We're not necessarily talking about the main ocean dozens of kilometers down, but about smaller pockets of liquid water that could exist much, much closer to the surface, perhaps only a kilometer or two deep in some places. This completely changes the game for exploration. Accessing liquid water a kilometer down, while still a monumental engineering challenge, is a far more conceivable prospect than trying to penetrate 30 kilometers of solid ice. These double ridges, therefore, are not just random scratches on the surface. They are potential skylights, natural pointers created by the Moon itself, indicating where the ice is thin and where liquid water might be nearest the surface. They are the signposts left by Europa, guiding future missions to the most promising places to search for signs of life. For all the incredible insights we've gained from studying Europa's surface, the most breathtaking revelation came not from staring at the ice, but from looking just above it. Imagine the scene, a brilliant, frozen world hanging in the blackness of space, and suddenly, from deep fractures near its south pole, immense geysers of water vapor blast hundreds of kilometers high, momentarily creating a tenuous, sparkling atmosphere against the void before particles fall back as snow or escape into space. This isn't a concept from a film. It's a real, observed phenomenon that has sent shockwaves through the scientific community. The discovery of these plumes effectively rewrote the entire playbook for exploring Europa, turning a distant, enigmatic moon into an active, dynamic world that seems to be actively reaching out to us. The first tantalizing hints emerged from data collected by the Hubble Space Telescope, our eye on the cosmos orbiting Earth. On multiple occasions between 2012 and 2015, Hubble's sensitive instruments detected something extraordinary, an excess of hydrogen and oxygen atoms, the components of water, scattered above Europa's southern hemisphere. The pattern was unmistakable. It suggested that brief, powerful eruptions were venting water vapor from below the ice shell, ejecting it with such force that it reached far into space. This was a monumental claim, and the scientific community, rightly cautious, demanded more evidence. Remarkably, that evidence was found by looking back through old data from the Galileo mission, which had ended nearly a decade before Hubble's observations. As scientists reanalyzed Galileo's magnetic field and plasma wave data from its close flyby of Europa in 1997, they found a curious signature. The spacecraft had briefly detected a change in the magnetic field and a spike in plasma density during its pass, which perfectly matched what you would expect if Galileo had accidentally flown through a column of ejected water vapor. The plume had been there all along, hidden in the data, waiting for us to understand what we were seeing. This discovery of active cryovolcanism is arguably one of the most significant in modern planetary science. These are not gentle steams, they are powerful, sporadic jets, possibly driven by the same tidal forces that heat the interior. The working theory suggests that as the ice shell flexes and cracks, the enormous pressure built up in the subsurface ocean or in shallow liquid water pockets finds a release valve. Water from these reservoirs forces its way up through newly formed fractures and, free from the confining pressure of the overlying ice, explodes into the vacuum of space in a spectacular plume. The material then follows a graceful arc, with some particles achieving escape velocity and drifting away, while most fall back to the surface, painting the terrain around the vent with a fresh, faint layer of frost. This process creates a direct, albeit temporary, atmospheric envelope that scientists call an atmosphere, further emphasizing the Moon's incredible activity. The implications for the search for life are nothing short of revolutionary. Before this discovery, the prevailing assumption was that to sample Europa's ocean, we would need to orchestrate a mission of almost unimaginable complexity, landing on the treacherous, radiation-blasted surface, then drilling or melting through up to 30 kilometers of ice, a technological hurdle we are still decades from overcoming. The plumes change everything. They offer a free sample delivered directly to us. A spacecraft could simply fly through the ejected vapor and, with the right instruments, analyze its composition in real time. We could look for complex organic molecules, salts that indicate a salty ocean interacting with a rocky seafloor, and perhaps even more direct indicators of biological processes. It provides a way to taste the ocean without ever having to crack the ice. This isn't just a convenient shortcut, it's a paradigm shift that has fundamentally shaped the design and objectives of the next generation of missions destined for this fascinating world. So the question becomes, if this ocean exists, what is it actually made of, and could its chemistry possibly support life? The clues we have point toward an environment that is not just habitable in theory, but potentially incredibly rich and complex. The most compelling evidence for its composition comes from those magnificent plumes themselves. When scientists analyzed the data from Hubble and the revisited Galileo information, they weren't just seeing water vapor. Spectroscopic analysis suggested the plumes also contained simple salts, like sodium chloride and magnesium sulfate, essentially table salt and Epsom salt, as well as what appear to be clay-like minerals. This is a huge deal because it tells us that Europa's ocean isn't just pure water. It's a salty brine, much like Earth's oceans, and it's clearly interacting with a rocky seafloor. This interaction between water and rock is the cornerstone of potential habitability. We believe Europa has a metallic core surrounded by a rocky mantle, which is then encased by this global ocean and its icy shell. The process of tidal heating doesn't just generate warmth, it also drives geological activity on that seafloor. This opens the door to one of the most exciting possibilities in astrobiology: hydrothermal vent systems. On Earth, in the absolute darkness of our deepest ocean trenches, hydrothermal vents are oases of life. They form where seawater seeps down into cracks in the ocean crust, is superheated by magma below, and then comes spewing back out, loaded with dissolved minerals and chemicals like hydrogen sulfide, methane, and hydrogen. The incredible part is that entire ecosystems thrive in these places, completely independent of sunlight. The base of the food chain isn't photosynthesis, but chemosynthesis, where microbes use the chemical energy from these vent fluids to create organic matter. Large organisms like tube worms and giant clams then feed on these microbes. If this same process is occurring on Europa's seafloor and all the ingredients are there, it could be providing both the energy and the nutrients needed to sustain life. The hydrogen and sulfates coming from the rocks could serve as a potent fuel source for microbial life, initiating a chemical reaction that releases energy, a process similar to what we see in some of Earth's most ancient extremophiles. Beyond the vents, the very chemistry of the ocean itself could be fostering life. The radiation bombarding the icy surface doesn't just stop at the ice. It creates a cascade of chemical reactions, generating molecules called oxidants. Remember the process of the ice shell recycling itself. Those oxidants from the surface could be getting mixed back down into the ocean through the churning ice. Once in the water, they could react with other chemicals like the sulfides rising from the vents below, creating a natural battery, a gradient of chemical energy that life could potentially exploit. This sets up a powerful scenario where energy is delivered from above and below, creating a mixing pot of ingredients that could make Europa's ocean not just a stagnant pool, but a dynamic, life-supporting environment. The combination of liquid water, a rich chemical soup, and multiple sustained energy sources moves this distant moon from a place of simple curiosity to arguably the most promising address for life beyond Earth we have yet discovered. For life to thrive anywhere, it needs a consistent source of energy, a fuel to power the incredible machinery of biology. Here on Earth, for almost every ecosystem we can see, that energy comes from one place, the sun. Plants capture sunlight and convert it into chemical energy through photosynthesis, and then every other creature, from the smallest insect to the largest whale, ultimately depends on that process. It's a system so fundamental to our existence that for the longest time we assumed it was a universal rule. The search for life elsewhere was therefore a search for places warm enough for liquid water and close enough to a star to bask in its light. This belief neatly placed a boundary around our hopes, limiting the potentially habitable real estate in our solar system to a narrow band where Earth orbits. But in the late 1970s, that entire worldview was spectacularly overturned, not by looking up at the stars, but by looking down into the deepest, darkest trenches of our own oceans. Scientists piloting the submersible Alvin were exploring a volcanic ridge deep in the Pacific Ocean, a place of crushing pressures and eternal night. There, miles below the surface where any hint of sunlight vanishes, they made one of the most profound discoveries in human history. Lush, thriving, bizarre ecosystems clustered around jets of superheated, mineral-rich water spewing from the seafloor. These are hydrothermal vents, and they host immense tube worms, ghostly white crabs, vast beds of clams, and other life forms existing in stunning abundance. This was life, but not as we knew it. It was an ecosystem operating on an entirely different power grid. The base of this entire food chain is not photosynthesis, but a radical process called chemosynthesis. Instead of using the energy of photons from the sun, specialized microorganisms, often called chemosynthetic bacteria, use the energy stored in chemicals. At these vents, seawater seeps down through cracks in the ocean crust where it is heated by the Earth's magma and becomes enriched with dissolved minerals and gases like hydrogen sulfide. When this superheated fluid erupts back into the cold ocean water, the bacteria perform their magic. They use the chemical energy released from the reaction between hydrogen sulfide and oxygen to produce organic matter, effectively creating food from poison and geological heat. These microbes are the grass of this sunless prairie, and everything else, from the worms that farm them inside their bodies to the crabs that scavenge the area, depends on this chemical energy harvest. This discovery shattered the paradigm. It proved that life is far more resourceful and resilient than we ever imagined. It demonstrated that the one ingredient absolutely crucial for a living world is not sunlight, but a sustained energy gradient, a reliable difference in energy that life can exploit. And this is the key that potentially unlocks Europa. We know Europa has a salty ocean. We know it has a rocky seafloor heated intensely by the constant tidal flexing from Jupiter's gravity. The conditions are practically perfect for the existence of hydrothermal vent systems just like those on Earth. If those vents are there, then the entire chain of life becomes a possibility. Chemosynthetic microbes could be thriving there right now, using the chemical energy from the vent fluids, perhaps hydrogen, methane, or sulfides, to build their cells. And if there are microbes, then more complex organisms could have evolved to feed on them, creating a full, if utterly alien, ecosystem in the eternal darkness. The entire concept of a habitable zone around a star becomes obsolete. We must instead think in terms of energy-rich environments, and Europa's hidden ocean may be one of the most energy-rich places we can imagine. If life can flourish around superheated vents in our own ocean's abyss, powered by chemistry alone, what other extreme examples on Earth might serve as a blueprint for what could be waiting in the darkness of Europa? To answer that, we don't need to look to the stars, but to our own planet's most hostile corners, where life doesn't just survive. It thrives in conditions we once thought were utterly sterile. These incredible organisms are called extremophiles, lovers of the extreme, and they are living proof that the parameters for life are far wider and more astonishing than we ever dreamed. Perhaps the most famous of these biological marvels is the tardigrade, also known affectionately as the water bear or moss piglet. This microscopic, eight-legged animal is nearly indestructible, a testament to life's stubborn will to persist. Tardigrades can be found in the most mundane places, like a patch of moss in your backyard, but their superpowers are anything but ordinary. They can withstand temperatures just a fraction of a degree above absolute zero, all the way up to well above the boiling point of water. They can survive pressures 6 times greater than those found in the deepest ocean trenches and thousands of times more radiation than a human could endure. They can even go without water for decades, entering a state of suspended animation called cryptobiosis, where they dehydrate their bodies and curl into a tiny, lifeless seeming ball called a ton, only to reanimate and stroll away when water returns. While a tardigrade itself is unlikely to be swimming in Europa's ocean, its existence demonstrates the incredible biochemical toolkit life can evolve to handle environmental extremes that mirror the punishing radiation, cold, and pressure of an icy moon. But for a more direct analog to what might be living on Europa, we return to the deep, to the tube worms and their microbial partners at hydrothermal vents. These creatures are not just tolerating their environment, they are perfectly adapted to it. They flourish under the immense, crushing weight of kilometers of ocean water, in total darkness, surrounded by water that is both superheated by the vents and near freezing just a short distance away, all while bathed in water laced with toxic chemicals like hydrogen sulfide. The giant tube worm, Rifsha is a particularly stunning example. It has no mouth, no gut, no digestive system at all. Instead, it survives through a symbiotic relationship with chemosynthetic bacteria that live inside its body. The worm provides the bacteria with the chemicals they need from the vent fluid, and the bacteria, in turn, provide the worm with all the organic nutrients it needs to grow, sometimes to over 2 meters in length. This is a complete, self-contained ecosystem that operates entirely independently of the sun, a powerful model for how a complex food web could be supported in Europa's dark, volcanically heated ocean. Beyond the deep sea, other extremophiles push the boundaries even further. In dark, sunless caves, microbial colonies survive by feeding on the rock itself, deriving energy from the chemical reactions between water and minerals like pyrite. In the bitter cold of Antarctic dry valleys, microbes live within the rocks, finding tiny pockets of liquid water in the ice. There are even bacteria like Deinococcus radiodurans that can repair their own DNA with incredible efficiency after being blasted with radiation that would shatter the genetic code of any other organism. Each of these organisms is a data point expanding our understanding of the habitable universe. They prove that life is not a fragile anomaly, but a potent and persistent force that can take root in the most unforgiving environments, so long as three key things are present: liquid water, a source of energy, and the right chemical building blocks. And this is why the extremophiles of Earth are so much more than just a biological curiosity. They are our most crucial guidebooks. They provide the tangible, empirical evidence that the conditions we infer exist on Europa, the cold, the pressure, the darkness, the chemistry, are not insurmountable barriers to life. In fact, they are conditions that life on Earth has already conquered. The leap from a superheated, sulfidic vent 2,000 meters under the Atlantic to a hypothetical vent on the seafloor of Europa no longer seems like a giant, imaginative stretch, but a logical extension of a principle we know to be true. These earthly extremophiles bridge the gap between the fantastic and the possible, transforming Europa from a mere subject of scientific speculation into a genuine candidate for a second Genesis. A world where the rules of biology, forged in fire and ice right here at home, might just be playing out again. This incredible possibility that we might not be alone in our solar system comes with a profound and sobering responsibility. As we prepare to send our most advanced robotic explorers to Europa, we are faced with a critical ethical question. How do we ensure that in our quest to discover life, we don't accidentally become the vector that destroys it or forever muddles our ability to recognize it? This isn't science fiction, it's the very real, meticulously planned field of planetary protection, and it forms the bedrock of all modern exploration beyond Earth. The core principle is simple in concept but incredibly complex in execution. We must protect other worlds from contamination by Earth life, and we must protect Earth from any potential extraterrestrial organisms we might bring back. The fear is not that a microbe from Earth would intentionally invade Europa, but that one would hitchhike there by accident. Our spacecraft are assembled in some of the cleanest rooms on the planet, but they are not sterile. Despite our best efforts, they can harbor incredibly resilient bacterial spores that cling to surfaces, hiding in tiny screws, cables, and circuit boards. These are the extremophiles we just discussed, organisms that can withstand the vacuum of space, intense radiation, and extreme temperatures. If a spacecraft like Galileo, which ended its mission by crashing into Jupiter, or a future lander were to carry even a single, hardy Earth microbe to Europa, and if that microbe were to find its way into the ocean through a crack or plume, the consequences could be catastrophic. It could outcompete any native life, consuming the precious chemical resources before we ever get a chance to study them. Or worse, it could simply exist, proliferating and making it impossible for us to ever know if the life we eventually detect is truly alien or just an invasive species from our own backyard. We would forever lose the opportunity to answer one of humanity's oldest questions with any certainty. To prevent this nightmare scenario, space agencies like NASA adhere to incredibly strict international protocols set by the Committee on Space Research. For a mission to a place like Europa, which has the highest potential for life, the requirements are extreme. The entire spacecraft must be built in a way that minimizes the number of microbial stowaways from the very beginning. Every component is meticulously cleaned with solvents and alcohol. The final assembled craft is then often baked in a special oven at high temperatures for extended periods, a process that kills the vast majority of any remaining organisms. For the Europa Clipper mission, which will conduct dozens of flybys, engineers have gone to extraordinary lengths. The trajectory itself is a key part of the protection plan, by never landing, and instead using Jupiter's immense gravity to eventually pull the spacecraft in to be destroyed. The risk of contaminating the Moon is kept extremely low. But even with that, the parts of the spacecraft that could potentially come into contact with the Moon, or that might harbor microbes in hard-to-sterilize places, are built with an additional layer of security. This is where the concept of bioburden comes in. Every square centimeter of the spacecraft is assigned a maximum allowable number of bacterial spores. For sensitive instruments, this number is virtually zero. This means that some of the most delicate and important tools, the ones designed to sample plume material or analyze surface composition, are subjected to the most rigorous sterilization processes to ensure they are as pristine as the environment they are meant to study. It's a monumental engineering challenge, balancing the need for absolute cleanliness with the need to build complex, functional machinery that can survive the journey and perform its duties. The goal isn't to achieve impossible perfection, but to reduce the probability of contamination to an acceptably tiny margin, a calculated risk that the international scientific community agrees upon. This painstaking, behind-the-scenes work is what makes modern exploration ethical and sustainable, ensuring that the worlds we visit remain pristine for future generations of scientists and perhaps for their own native inhabitants. With our understanding of Europa built from decades of distant observations and brilliant deduction, the stage is now set for the next monumental leap, a dedicated, state-of-the-art mission designed to turn compelling hypotheses into confirmed fact. This is NASA Europa Clipper, an orbiter of astonishing capability being prepared for a journey that will fundamentally rewrite our understanding of this enigmatic world. Unlike any mission before it, Clipper is not merely a flyby. It is a holistic habitability investigator, engineered from the ground up to answer the most pressing questions about that hidden ocean, the icy shell that conceals it, and the potential for life within. Scheduled to launch no earlier than October of 2024 aboard a powerful SpaceX Falcon Heavy rocket, the spacecraft will begin a long, looping journey through the inner solar system, using gravity assists from Mars and Earth to slingshot itself toward the Jovian system. This intricate path saves an immense amount of fuel, but more importantly, it allows the spacecraft to arrive at Jupiter with a trajectory carefully calculated for its primary mission. To conduct nearly 50 close flybys of Europa over several years, each pass bringing it soaring just 25 kilometers above that fractured, icy landscape. This repeated dance is a masterstroke of orbital planning. By never entering a permanent orbit around Europa itself, which would bathe the spacecraft in the Moon's intense radiation belts and shorten its life, Clipper can instead use Jupiter's gravity to swing back for pass after pass after pass, systematically mapping the entire globe at unprecedented resolution from a variety of angles and lighting conditions. The true power of this mission, however, lies in its incredible suite of 9 dedicated instruments, a scientific arsenal working in concert to perform a complete diagnostic of the Moon. These tools can be broadly grouped by their function: those that will study the ice shell and the ocean beneath it, those that will analyze the composition of the surface and any plumes, and those that will image the surface in stunning detail to understand its geology. For probing the depths, a powerful ice-penetrating radar will send signals into the crust, mapping the structure of the ice down to many kilometers and hunting for the Holy Grail, direct evidence of those suspected shallow water pockets, potentially located just a few kilometers below the surface. A magnetometer will perform a far more precise version of the measurements Galileo made, characterizing the ocean's depth, salinity, and thickness of the ice shell above it by studying the induced magnetic field. When Clipper flies through one of those sporadic water plumes, its mass spectrometers will come to life, acting as chemical laboratories that will taste and analyze the vapor and any dust particles, searching for the telltale signatures of organic molecules, salts, and other compounds that could indicate a life-friendly environment below. Cameras will map most of the surface at a resolution of better than 50 meters per pixel, with detailed shots of key areas like chaos terrain and fractures reaching an incredible 0.5 meter per pixel, allowing us to see features the size of a dinner table. This immense volume of data will be streamed back to Earth via a massive 3-meter-wide high-gain antenna, painting a picture of Europa so detailed it will feel less like discovery and more like revelation. Every measurement, every spectral signature, every radar echo is a single piece of a puzzle, and Europa Clipper is designed to collect them all, finally allowing us to see the full, breathtaking picture of a world that may be the closest thing we have to a living planet beyond our own. While NASA Europa Clipper focuses its powerful instruments on the enigmatic ice moon, it won't be working alone in the Jovian system. The European Space Agency is mounting its own ambitious expedition to the Jupiter system, a mission named Jupiter Icy Moons Explorer, or JUICE. This parallel endeavor represents a brilliant symphony of international planetary science, where two distinct missions are orchestrated to perform a grand duet, each with its own part to play in unraveling the mysteries of these watery worlds. Where Clipper is a specialist designed for an intense, targeted study of Europa, JUICE is more of a system-wide naturalist, embarking on a broader tour to compare and contrast not just Europa, but two other colossal moons, Ganymede and Callisto. The core of JUICE mission is a profound and fascinating question: what makes a moon habitable? By studying 3 different moons that all likely contain subsurface oceans, scientists can move beyond the specifics of a single world and start to understand the universal principles that govern the emergence and sustainability of life in icy environments. Europa, with its young, active surface and likely thin ice shell, represents one extreme, a dynamic and potentially highly energetic environment. Callisto, ancient and heavily cratered, appears to be a fossil world, a glimpse into an early solar system object where any subsurface ocean might be quiet and isolated. And then there's Ganymede, the largest moon in the solar system and JUICE's ultimate prize, a world so unique it possesses its own intrinsic magnetic field, a trait shared only with Mercury and Earth. This comparative planetology approach is why JUICE's flight plan is so different. After a series of flybys of Europa and Callisto to gather critical data, the spacecraft will eventually do something no probe has ever done before. It will enter orbit around Ganymede for an extended, close-up study. This final act will transform our understanding of this giant moon, mapping its surface, probing its interior ocean, and studying how its magnetic field interacts with the powerful magnetosphere of Jupiter itself. The data from this trio of moons will provide a powerful control group. By seeing how these oceans and ice shells behave under different levels of geological activity, tidal heating, and radiation, we can finally begin to understand which conditions are truly essential for life and which are merely incidental. The real magic, however, will happen when the datasets from Clipper and JUICE are combined. Imagine 2 master cartographers, one mapping a coastline in exquisite detail and the other charting the entire continent. Only when their maps are laid side by side does the full geography become clear. The 2 missions carry different but deeply complementary instrument suites. For instance, both have ice-penetrating radars, but they operate at different frequencies. Clipper's radar is tuned to penetrate shallower ice, perfect for hunting those near-surface water pockets on Europa. JUICE radar is designed for deeper penetration, ideal for gauging the overall thickness of Ganymede's icy shell. By comparing the radar returns from both moons, scientists can develop a much more robust model of how ice behaves under different conditions across the entire solar system. Their synergy extends beyond the ice. Both spacecraft carry powerful tools to sample the tenuous atmospheres and any potential plumes. If one craft detects a plume eruption on Europa, it can alert the other, potentially allowing for a second, confirming observation from a different angle or with a different set of instruments. Their combined magnetometer data will allow for an unprecedented three-dimensional mapping of Jupiter's magnetic field and its interaction with the moons, giving us a far clearer picture of the oceans hidden below. This isn't a race or a competition, it's a collaborative effort on a cosmic scale. The missions were developed in tandem, with scientists from both teams sharing information to ensure their investigations would dovetail perfectly. The result will be a holistic portrait of the Jovian system that is infinitely richer, more detailed, and more profound than anything either mission could achieve alone, turning two separate journeys into a single, unified quest to answer one of humanity's oldest questions. But the true ambition, the mission that would represent the absolute pinnacle of exploration, lies beyond orbiters and flybys. It's the dream of a Europa lander, a robotic emissary designed to do the unthinkable, touch down on that fractured alien ice and search for the signs of life directly. This is a concept that moves us from remote observation to intimate contact, and it presents a set of engineering and scientific challenges so immense they border on the fantastical. The first and most immediate hurdle is simply landing safely. Europa's surface is not a smooth, welcoming plain. It's a jagged, chaotic labyrinth of ice blocks, towering ridges, and gaping fractures. Placing a delicate spacecraft gently onto this treacherous terrain requires a level of autonomous navigation far beyond anything we've attempted before. Imagine the descent. The lander, having separated from its orbiting mothership, would fire its retro-rockets to begin a controlled fall, but it can't rely on pre-programmed coordinates alone. In its final minutes, its computer brain would need to analyze the landing site in real time using high-resolution cameras and LiDAR, comparing the terrain below to onboard maps to identify the one flat, stable spot amidst a field of deadly shards and crevices. It would have to perform a complex rocket-powered dance, hovering, translating sideways, and finally touching down with utter precision on a surface we have only seen from afar. All of this must happen with a significant time delay from Earth, making remote control impossible. The lander must think for itself, and its success would be a breathtaking testament to autonomous robotic intelligence. Once securely on the surface, its real work begins, operating in one of the most punishing environments known to science. The lander would be bathed in intense radiation from Jupiter's magnetosphere, requiring heavily shielded electronics to survive even a short mission. Its instruments would need to be miniaturized, hardened, and incredibly robust to function in temperatures hundreds of degrees below freezing. The primary goal would be to search for biosignatures, any substance or pattern that provides scientific evidence of past or present life. This isn't about finding alien fish, it's about hunting for the microscopic and molecular clues that life leaves behind. The most capable tool for this hunt would be a sophisticated drill or melt probe, designed to penetrate the ice, either mechanically or by using heated tips to melt downward. This isn't about reaching the ocean, that goal remains for a far future generation. Instead, this drill would aim to retrieve pristine ice cores from depths of a few meters to perhaps a dozen meters, far enough down to be shielded from the sterilizing radiation that bombards the surface. Within these ice samples, scientists hope to find a frozen record of history. Material from the subsurface ocean or from those shallow water pockets could have been forced upward through cracks and plumes over millennia, becoming trapped and preserved in the icy matrix like insects in amber. A lander's drill could retrieve this precious time capsule and feed it into a miniaturized onboard laboratory. This laboratory would be a marvel of analytical chemistry, containing instruments like a Raman spectrometer to identify molecular bonds, a laser desorption mass spectrometer to vaporize tiny samples and weigh their constituent molecules, and most tantalizingly, a high-resolution microscope capable of imaging any potential microorganisms or their fossilized remains. It would search for the building blocks of life, complex organic molecules like amino acids and lipids, but more importantly, it would look for patterns that cannot be easily explained by geology alone. It would seek an imbalance in molecules that are typically symmetrical in non-living chemistry, a preference for one-handedness over another, a signature that screams biology. Rather than mere chemistry, finding a single, complex cell frozen in the ice would be a discovery that would eclipse every achievement in human history, a moment that forever divides our story into a before and an after. The Europa lander represents our deepest yearning to not just infer the possibility of life, but to reach out and touch it. Confronting that immense barrier of ice represents perhaps the most audacious engineering challenge humanity has ever contemplated. We're not talking about a simple drill rig. We are envisioning a robotic mission to autonomously penetrate a frozen alien crust that could be as thick as Mount Everest is tall, all to deploy a submersible into a pitch-black ocean under crushing pressure, with no hope of retrieval or repair. The scale of this endeavor is almost beyond comprehension, yet scientists and engineers are already developing and testing the incredible machines that could one day make it a reality. The leading concept for this monumental task is known as a Cryobot, a cylindrical probe designed to essentially melt its way straight down. The principle seems deceptively simple at first glance. Heat a metal tip to a very high temperature and use it to melt the ice, allowing the probe to sink downward as the water refreezes behind it. But the devil, as always, is in the cosmic details. A Cryobot couldn't just be a simple hot rod. It would need to be a fully self-contained, intelligent laboratory, packed with power systems, communication equipment, and scientific instruments, all while being tough enough to handle unknown obstacles and conditions. The journey downward would be a voyage into the complete unknown. The probe might encounter layers of pure ice, gritty with embedded rocks or salts that could impede its progress. It could hit pockets of trapped gas or find itself navigating through slushy, partially melted zones that behave unpredictably. Engineers are developing sophisticated sensors for these probes, using forward-looking radar and sonar to see several meters ahead, allowing the Cryobot to adjust its path or melting power to avoid hazards long before it encounters them. Powering this multi-kilometer descent is another monumental hurdle. The energy required to melt that much ice is staggering. One proposed solution is to use a compact nuclear fission reactor, a miniature power plant that could provide a steady, immense amount of heat for the melting tip and electricity for the onboard systems for months or even years. This isn't science fiction. NASA is actively developing such technology through its Kilopower project. As the probe descends, it would leave behind a trail of cabling, a fragile umbilical cord connecting it to a surface lander. This lander would act as a communication relay, beaming the precious data from the depths back to Earth. The refreezing ice behind the Cryobot is both a blessing and a curse. It securely anchors the cable in place, but it also means that once the probe goes down, it can never come back up. The ultimate prize, the moment the entire mission builds toward, arrives when the Cryobot's sensors finally detect a change. The ice gives way, and the probe plunges from a world of solid confinement into the liberty of a liquid ocean. At this point, the Cryobot would become a stationary sentry, a docking station and data relay perched at the ocean's ceiling. It would then deploy its passenger, a free-swimming autonomous underwater vehicle often called a hydrobot. This submersible, untethered and free to explore, would be our eyes and hands in the abyss. Designed to be neutrally buoyant in the alien sea, it would use a combination of thrusters and ballast systems to navigate the currents, its floodlights piercing the eternal darkness for the first time in history. Its suite of instruments would be a marvel of miniaturization: high-definition cameras, chemical and organic molecule sensors, mass spectrometers, and samplers to collect water and any particulate matter. Its primary mission would be to hunt for life, not by looking for great sea monsters, but by searching for the microscopic and chemical clues of a biological presence. It would analyze the water's composition, measure energy gradients, and perhaps even use a laser to excite molecules in a sample, looking for the distinctive fluorescent glow that might be emitted by organic compounds. The sheer ambition of such a mission forces us to think generations ahead. This isn't a project for a single decade. It is a goal that will require sustained international collaboration, technological leaps, and unwavering political will. The payoff, however, is immeasurable. To see the first images stream back from that hydrobot, not of barren water, but of a complex ecosystem thriving around a hydrothermal vent, with strange, beautiful organisms living their lives in absolute isolation from the sun, would be a moment that transcends science. It would be a profound, universe-altering revelation, proving that the spark of life is not a singular accident on one tiny world, but a fundamental force of nature, waiting to be kindled wherever the conditions are right. The technical challenges of drilling through the ice are immense, but they are the key to unlocking what may be the greatest discovery in the history of our species. Speculating on the actual forms life might take in Europa's sunless abyss is where compelling science meets the deepest reaches of our imagination. Without the guiding hand of sunlight, evolution on this icy moon would be forced to navigate a radically different set of rules, sculpting life from the raw materials of chemistry, pressure, and darkness. To envision what might be swimming in those black waters, we must look to the closest parallels we have on our own planet, the astonishing ecosystems thriving in the eternal night of Earth's deep oceans, particularly around hydrothermal vents. The most basic and likely form of life would be microbial, existing in vast, sprawling mats that coat the rocky seafloor around hydrothermal vents. These would not be simple bacteria, but complex communities of chemosynthetic organisms, the foundational crop of this alien world. They would harness the chemical energy from the vent fluids, perhaps metabolizing hydrogen sulfide, methane, or hydrogen, to synthesize organic matter, forming the base of a food web utterly independent of photosynthesis. We might find these microbial communities living not just on rocks, but even floating as a kind of marine snow in the water column, a constant drizzle of organic material falling through the darkness, providing a nutrient source for other creatures. But the true fascination lies in the possibility of more complex multicellular life. On Earth, vent systems support a stunning array of animals that have evolved to exploit this chemical energy. The most likely Europan analogues might be something akin to tube worms, but they wouldn't look exactly like Earth species. Without the need for a symbiotic relationship with bacteria inside their bodies, a highly specific evolutionary adaptation, Europa's complex life might be simpler. We could see filter feeders, perhaps gelatinous and delicate, drifting through the water to harvest the suspended microbial matter. They might appear as ethereal, pulsating bags of jelly, using tiny cilia to create currents that draw food into their simple digestive systems. Their bodies would likely be soft and flexible to withstand the immense pressure, lacking hard skeletons or shells which require specific minerals that might be scarce. The sensory world of these creatures would be entirely alien. In the absolute blackness, eyes would be useless unless they evolved for a different purpose entirely. Instead, life might rely on sophisticated sensors for detecting subtle changes in water pressure, chemical gradients, or electrical fields to navigate and find food or mates. This could lead to life forms covered in delicate, hair-like cilia or intricate lateral line systems far more sensitive than anything found on Earth. And then there is the captivating potential for bioluminescence, the ability to create their own light through chemical reactions. On Earth, in the deep sea, an estimated 90% of creatures are bioluminescent. They use light not for vision but for communication, to attract prey, to startle predators, to lure a mate in the overwhelming dark. In Europa's ocean, this could create a breathtaking underwater aurora. A predator might dangle a glowing lure from its head, while a shoal of smaller creatures could communicate with complex patterns of flashing lights across their bodies. The water itself might shimmer with the faint glow of uncountable microorganisms, a living galaxy swirling in the abyss. Their light shows would be a silent, beautiful language we are only beginning to imagine, a testament to life's drive to connect and communicate even in the most isolated of environments. The very biochemistry of Europan life could be fundamentally different. If the ocean is highly saline and rich in certain compounds, life might use alternative solvents to water or different molecular backbones for its structure. Perhaps instead of DNA, their genetic information is stored in a more stable molecule resistant to radiation that might seep down from the surface. Their cellular machinery might operate at a much slower metabolic rate due to the cold, leading to creatures that live for centuries, moving with a slow, graceful patience that is unimaginable to us. The possibilities are as endless as the ocean is deep, limited only by the laws of physics and chemistry, which we now know are incredibly permissive when it comes to life's ingenuity. So, if we can't simply send a submarine to look for alien fish, how will we actually know if we've found life? The answer lies in the subtle, chemical whispers that biology leaves behind, clues known as biosignatures. A biosignature is any substance or pattern that provides compelling scientific evidence for past or present life. It's not about finding a single, magic bullet molecule, but about assembling a body of evidence so consistent with biology and so difficult to explain by geology alone that life becomes the only logical conclusion. The search is a meticulous process of cosmic forensics, and scientists have a detailed checklist of what to look for. The first and most fundamental clue would be an imbalance, a striking irregularity in the ratios of certain elements or molecules. In the non-living world, chemistry tends toward symmetry and balance, but life is inherently messy and selective. It has preferences. A powerful example is something called chirality or handedness. Many complex organic molecules, like amino acids, the building blocks of proteins, can exist in two mirror image forms like a pair of gloves. Abiotic processes, like those in a laboratory or on an asteroid, tend to create a 50-50 racemic mixture of both left-handed and right-handed versions. Life, however, almost always chooses one. All known life on Earth uses exclusively left-handed amino acids to build proteins. If a future lander were to drill into Europa's ice and find a sample teeming with amino acids that are overwhelmingly left-handed or overwhelmingly right-handed, that would be a screaming red flag. Such a pronounced imbalance is incredibly difficult to achieve without the influence of biology. It would suggest that a living process was selectively using one type and discarding the other, a signature of life's efficiency and specificity. Beyond simple imbalances, scientists will be hunting for molecules of a certain complexity and structure that hint at a biological origin. Finding simple methane or carbon dioxide isn't enough. Those can be produced easily by geological activity. The real excitement comes from discovering complex organic molecules, especially ones that are arranged in patterns that suggest they were once part of a living system. Lipids, for instance, are the molecules that make up cell membranes. On Earth, these molecules have very specific chain lengths and structures that allow them to form stable, protective barriers. Finding a suite of lipids with those same specific characteristics in a Europan ice sample would be incredibly suggestive. Similarly, finding molecules like porphyrin's complex ring structures that form the core of chlorophyll in plants and hemoglobin in our blood would be another strong indicator, as these are large, intricate molecules that are central to energy transfer in living systems and are not known to form easily without biological processes. Perhaps the most convincing evidence of all would be the discovery of actual cellular structures or fossils. A microscope on a lander's robotic arm could reveal the ultimate prize, the physical remains of microorganisms frozen in time. But even here, scientists must be cautious. Some mineral formations can create tiny structures that look eerily like bacterial cells. The key is to look for evidence of complexity that can't be forged by geology. This means looking for cells that are all a similar size and shape, suggesting they are part of a population. It means looking for evidence of cell division, where one cell appears to be pinching into two. It means looking for structures inside the cells, or for cells that are grouped together in chains or clusters, much like colonies of bacteria we see on Earth. Finding a physical structure that not only looks like a cell, but also shows these hallmarks of growth and reproduction would provide evidence that is nearly impossible to refute. Ultimately, the case for life on Europa won't be made on a single discovery. It will be built upon a convergence of evidence, a compelling narrative written in chemistry and form. It will be the combination of a chirality imbalance, the presence of complex lipids and porphyrins, and the visual identification of cellular structures, all found together in a context that makes sense, like a sample taken from a region known to be geologically active. Scientists will have to rule out every possible non-biological explanation for this suite of evidence. It's a painstaking process, but one that is necessary for a claim of this magnitude. The goal is to be able to look at the data and say, with a high degree of confidence, that the simplest and most powerful explanation for everything we are seeing is that we are not alone. Finding life on Europa would do far more than just answer a scientific question. It would ignite a revolution in human thought as profound as when we first realized the Earth revolved around the Sun. This discovery would be the single most important event in the history of science, not because it would tell us we are not alone, but because it would tell us that we never were. The universe, we would learn, is brimming with life. The implications would ripple through every facet of our existence, from our deepest held beliefs to our most ambitious dreams for the future. Scientifically, it would be the ultimate confirmation of the principle of mediocrity, the idea that there is nothing particularly special or privileged about our position in the cosmos. For centuries, we have wondered if life on Earth was a miraculous, one in a trillion accident. Finding a second, independent genesis on a moon next door would shatter that notion. It would prove that the emergence of life is not a rare, fragile miracle, but a natural and even probable process wherever the right conditions exist: liquid water, a source of energy, and the right chemistry. This realization would instantly transform astrobiology from a speculative field into a hard science, with a concrete data point proving that life can and does arise elsewhere. Our search for life would explode in scope and urgency. Every icy moon in our solar system, Enceladus, Titan, Ganymede, would instantly become a prime target. The number of potentially habitable exoplanets in our galaxy would leap from a speculative maybe to an overwhelming almost certainly. We would stop asking if life is out there and start asking what kind, how much, and where exactly it can be found. The philosophical and theological tremors from such a discovery would be even more profound. It would force a fundamental re-evaluation of humanity's place in the grand scheme of existence. For many, it would be a humbling and awe-inspiring expansion of creation, a testament to the incredible creativity and abundance of the universe or a divine creator. For others, it would challenge the very foundations of belief systems that place humanity at the center of a cosmic story. The question of whether we are special, chosen, or unique would be answered with a resounding and unsettling no. We would have to come to terms with being just one thread in a vast cosmic tapestry of life. This could initially be a source of existential anxiety, a feeling of cosmic loneliness replaced by a feeling of cosmic smallness. But ultimately, it could foster a new planetary identity, uniting humanity as one species among many in a living universe. It would be the final, definitive step in the Copernican revolution, moving Earth from the center of the universe to the center of a solar system, to just one of countless homes for life. Practically, the discovery would reshape our future as a spacefaring species. It would instantly elevate planetary protection from a technical protocol to a sacred, species-wide imperative. If Europa has its own native biosphere, we would have an absolute ethical obligation to protect it from our contamination, treating it not as a resource to be exploited, but as a priceless wilderness to be preserved and studied with the utmost care. This new perspective would set a crucial precedent for how we interact with all other worlds, establishing a principle of cosmic stewardship. Furthermore, studying a second genesis of life would be like finding a second book of nature written in a completely different language. By comparing its biochemistry to our own, we could finally begin to understand which aspects of life are universal and which are merely local accidents of history. Does life always use DNA and proteins? Does it always have the same chiral preference? The answers could unlock the fundamental rules of biology, leading to unimaginable advances in medicine, genetics, and biotechnology here on Earth. A discovery on a distant moon would not just tell us about the universe, it would tell us about ourselves, finally giving us the context to understand what life truly is. This profound responsibility forces us to confront a deeply ethical dilemma, one that extends far beyond the technical challenges of planetary protection. If we were to discover a living, thriving ecosystem within Europa's ocean, completely isolated from the rest of the universe for billions of years, what right do we have to intervene? The question shifts from can we explore to should we, and the answer is not as simple as our curiosity might wish. We must weigh our insatiable drive for knowledge against the potential for irreversible harm, considering whether our role is that of an observer or a participant, and what moral duties come with being the first intelligent species to stumble upon this hidden world. On one side of this debate is the principle of non-interference, a perspective often compared to the prime directive from science fiction, but grounded in very real scientific conservation ethics. Proponents of this view argue that a Europan biosphere would be the most significant scientific discovery of all time precisely because it has evolved in total isolation. It represents a second, independent genesis of life, a separate experiment in biology that could teach us everything about the universal principles of life itself. Any contamination from Earth, whether accidental or through deliberate interaction, would forever ruin the pristine nature of this experiment. Introducing even a single Earth microbe could act like an invasive species, outcompeting and driving native life to extinction before we even understand it. Our mere presence, the heat and chemicals from our probes, could alter the delicate balance of this ecosystem. From this standpoint, the most ethical and scientifically valuable course of action is one of pure observation using remote sensors and perhaps even deploying sterile, passive monitors to study the environment without ever physically touching it, preserving this alien world as a sacred natural laboratory. However, the opposing viewpoint holds that such strict non-interference is both impractical and perhaps even a different kind of ethical failure. The very act of going to Europa and confirming the existence of life is in itself a monumental intervention that changes everything for that world. Once we know it is there, we cannot simply turn our backs and pretend we never found it. Furthermore, proponents of careful interaction argue that the potential benefits are too great to ignore. Understanding a second genesis of life could unlock breakthroughs in medicine, genetics, and our understanding of our own biology that could save countless lives on Earth. There is also a powerful argument from the perspective of stewardship. If we discover that Europa's ecosystem is fragile and on the verge of collapse due to some natural geological change, would we not have a moral obligation to intervene and prevent an extinction event? This line of thinking suggests that with knowledge comes responsibility, and that our advanced technology might one day be used not to harm, but to nurture and protect this alien life, becoming guardians rather than mere visitors. This debate is further complicated by the long-term specter of colonization and resource exploitation. While this may seem like the stuff of far future speculation, the history of human exploration on Earth suggests it is an inevitable consideration. Europa's ocean represents a vast quantity of water, a critical resource for any future deep space civilization. Would we have the right to mine this water, even if it meant disrupting or destroying native life? The current framework of international space law, primarily the Outer Space Treaty, states that celestial bodies are not subject to national appropriation and are to be used for the benefit of all mankind. But it says very little about protecting potential extraterrestrial ecosystems from commercial interests. This forces us to establish new precedents now, creating robust legal and ethical frameworks that prioritize the preservation of alien life over economic or political gain, ensuring that Europa does not become a cosmic tragedy of the commons. Ultimately, our approach to Europa may define our character as a species as we step onto the cosmic stage. Will we be the careful archivists of the galaxy, preserving its wonders with a respectful distance? Or will we be active gardeners, nurturing life wherever we find it and using our knowledge to foster its growth? The most prudent path likely lies somewhere in between a doctrine of cautious, minimal, and reversible interaction. This means any mission designed to make direct contact must be planned with the utmost caution, incorporating technology that can be sterilized to an almost impossible standard and having contingency plans to withdraw at the first sign of unforeseen consequences. It means that every action we take must be preceded by the question not just of what we can learn, but of what we might irrevocably lose. The silence of Europa's ocean has held its secrets for eons. Our first communication with it should be a whisper, not a shout, ensuring that our legacy is one of wisdom and reverence rather than reckless curiosity. But as we stand on the precipice of simply discovering what lies within Europa's ocean, it's almost irresistible for the human mind to push further, to dream bigger, and to ask the ultimate what if. What if we didn't just explore this alien sea, but attempted to remake it? What if we took this frozen, radiation-scoured world and transformed it into a second Earth, a blue and green paradise floating in the Jovian system? This is the breathtakingly ambitious concept of terraforming, and applying it to Europa moves us from the realm of hard science into a far future fantasy that challenges the very limits of our imagination and our ethics. The theoretical process for terraforming Europa would be an engineering project of such staggering scale it dwarfs anything humanity has ever conceived. The first and most monumental step would be to somehow melt the entire icy crust to unify the subsurface ocean with the surface, creating a single, globe-spanning aquatic world. This alone presents an energy requirement that is almost physically incomprehensible. One far-fetched idea involves using giant orbital mirrors, hundreds of kilometers across, to focus sunlight onto the surface and gradually heat it. But Europa receives only a fraction of the sunlight that Earth does, making this approach incredibly slow and inefficient. A more drastic and frankly terrifying proposal suggests deliberately redirecting comets or small icy moons from the outer solar system to crash into Europa's surface. The sheer kinetic energy from such a colossal impact would release an unimaginable amount of heat, potentially flash melting vast portions of the crust and ejecting enormous plumes of water vapor into space. This method, however, is the definition of a blunt instrument. It would be utterly unpredictable, likely devastating any existing ecosystem and turning the moon into a chaotic, boiling cauldron for centuries. Assuming we could somehow create this planet-wide ocean, the next challenge would be even more daunting, generating a stable, breathable atmosphere. Europa currently has only the most tenuous wisp of an exosphere, constantly stripped away by Jupiter's powerful radiation belts. To give it a real atmosphere, we would need to outgas enormous quantities of nitrogen, oxygen, and carbon dioxide. This could theoretically be done by redirecting thousands more volatile-rich comets to impact the surface, their ices vaporizing to contribute gases. But then we would face the constant battle against Jupiter's magnetosphere, which would relentlessly tear this new atmosphere away. The only conceivable solution would be to create an artificial magnetic shield, perhaps by placing a massive superconducting magnet at the Lagrange point between Jupiter and Europa, a feat of technology that belongs firmly in the realm of magic by our current understanding. Even if these physical miracles could be performed, the ethical hurdles are perhaps even more insurmountable. Terraforming Europa is fundamentally an act of planetary-scale violence. It presupposes that this world is a dead rock waiting for our touch, but everything we've discussed points to the opposite conclusion. Europa is almost certainly a living world with its own unique billion-year-old biosphere thriving in the dark. To melt the ice would be to commit absolute xenocide, boiling alive every last organism in a misguided effort to make a new home for ourselves. It would be the destruction of a second genesis of life for the convenience of a single species. This forces us to confront a profound philosophical question. Do we have the right to reshape other worlds in our own image, especially when they may already be inhabited? The value of Europa is not in its potential to be a second Earth, but in its profound and beautiful alienness. It offers us the chance to learn from a biology that took a completely different path, an opportunity that will be obliterated forever by terraforming. This dream of remaking worlds says more about our own restless ambition than it does about the silent, waiting ocean beneath the ice, an ocean that deserves not to be conquered, but to be understood on its own extraordinary terms. Imagine a spacecraft making its final approach to Europa, not with a human hand at the controls, but with an artificial brain capable of processing millions of data points in the blink of an eye to choose the only safe landing spot within kilometers of treacherous ice. This is not a distant fantasy, it is the imminent future of exploration where artificial intelligence transitions from a helpful tool to an indispensable partner. The immense distance between Earth and Jupiter creates a communication delay of up to 50 minutes each way. A command sent from mission control would take nearly an hour and a half to receive a confirmation, a timeline utterly incompatible with the split-second decisions required for a precision landing on a world of shattered terrain and sudden plume eruptions. This fundamental limitation is what makes advanced autonomous AI not just beneficial, but absolutely critical for any mission that hopes to touch down on Europa's surface and survive. The first and most dramatic application of this technology will be in the guidance systems of a future Europa lander. Current Mars rovers like Perseverance possess a degree of autonomy, but their navigation is largely a slow, cautious process guided by pre-planned routes from Earth. A Europa lander would need something far more advanced, a system of real-time hazard detection and avoidance that operates with a pilot's instinct. As the lander descends, its onboard AI would be fed a constant stream of information from LiDAR, radar, and high-resolution cameras. Its singular mission in those final, tense minutes would be to compare the terrain rushing up to meet it against incredibly detailed orbital maps stored in its memory, while simultaneously identifying new, unforeseen hazards, a hidden crevasse, a sharp ice spire, an unstable overhang. The AI wouldn't just be looking for a flat area, it would be evaluating the structural integrity of the ice, the angle of the slope, and the potential for the landing legs to find secure footing. It would need to make these life or death calculations in microseconds, executing a complex series of thruster burns to hover, translate sideways, and descend with a gentle precision that human operators millions of miles away could never hope to achieve. This level of machine independence represents a monumental leap in how we explore, trusting sophisticated algorithms to be our eyes, hands, and instincts on another world. Once safely on the surface, the AI's role shifts from pilot to scientist, and its tasks become even more complex. The primary objective of a lander mission would be to search for biosignatures, the chemical or structural hints of past or present life. The instruments designed for this hunt, like mass spectrometers and chromatographs, generate enormously complex datasets, far too vast and intricate to beam back to Earth in their raw form for scientists to slowly sift through. Instead, an onboard AI would act as a first-pass science team processing this data in real time. It would be trained on countless simulations and Earth-based examples to recognize patterns that are suggestive of biological activity. For instance, it could immediately identify a pronounced chiral imbalance in a sample of amino acids, a strong potential biosignature, or detect the unique spectral fingerprint of complex lipid molecules that are often associated with cell membranes. This isn't about the AI making a definitive declaration of life found, it's about intelligence amplification. The AI would flag anomalous, exciting, or high-priority results, allowing it to make an autonomous decision on what to do next. Should it drill here again for a deeper sample? Should it adjust its instruments to focus on a specific wavelength? Should it alert the orbiter overhead that this location is particularly interesting and warrants further study? This capability turns a static lander into an adaptive field researcher, capable of following the scientific evidence wherever it leads without waiting for a command from home that won't arrive for over an hour. This machine learning system would also serve as a crucial guardian for the mission itself and for the pristine environment it is studying. The AI would constantly monitor the lander's health, predicting potential system failures from subtle changes in power consumption or temperature readings long before they become critical, allowing for automated corrections. Perhaps most importantly, it would be the enforcer of planetary protection protocols. The AI could control the robotic arm and drill, ensuring that sterilization procedures are followed meticulously between samples to prevent any cross-contamination. It could even be programmed with an ethical constraint, a form of artificial conscience, that would prevent it from conducting an experiment or moving to a new location if its analysis determined the action posed an unacceptable risk of contaminating a potentially habitable zone. This transforms the AI from a simple tool into a responsible steward, embodying our highest ethical principles for exploration, even when direct human oversight is impossible. The journey to Europa will be one of the most ambitious we have ever undertaken, and it will be guided by the seamless partnership of human curiosity and artificial intelligence, working in concert to unlock the secrets of an alien ocean. This global effort, bringing together the brightest minds and most advanced technology from across our planet, truly underscores the monumental importance of the questions we're asking about Europa. It's a powerful reminder that this isn't a national competition, but a species-wide collaboration, a unifying project for all of humanity. NASA Europa Clipper and the European Space Agency's JUICE mission are the flagships of this endeavor, but their success is built upon a foundation of international contribution and shared knowledge. Scientists from Japan's JAX are providing critical instrument components and expertise, particularly in the analysis of dust and plasma particles that Clipper will encounter. Agencies from Canada and Israel are also contributing key hardware and software systems, turning these spacecraft into orbiting United Nations of scientific discovery. This spirit of cooperation extends far beyond government agencies, weaving in a global tapestry of academic and research institutions. Universities from the United Kingdom are deeply involved in modeling the dynamics of Europa's ice shell, while teams in Germany and France are leading the development of the powerful ice-penetrating radars that will peer into the Moon's depths. Researchers in Italy are working on sophisticated communication systems to handle the immense flow of data back to Earth, and Australian scientists are utilizing their vast radio telescope arrays, part of the Deep Space Network, to ensure we don't miss a single precious byte of information from 1 billion miles away. This isn't just a list of participants, it's a collective brain trust, a global hive mind focused on a single, profound objective. The collaboration is woven into the very fabric of the missions themselves. The trajectories of Clipper and JUICE were carefully planned to be complementary, not duplicative. data from one mission will directly inform and enhance the observations of the other, creating a holistic picture of the Jovian system that no single agency could achieve alone. This level of planned synergy is unprecedented. Scientists from every participating nation regularly meet, share preliminary findings, and publish research together, ensuring that the knowledge gained benefits all of humanity equally. This open exchange of ideas accelerates discovery, preventing the siloing of information and fostering an environment where a breakthrough in a lab in Switzerland can immediately influence an observation strategy for a spacecraft built in the United States. Perhaps the most beautiful aspect of this international partnership is how it mirrors the very nature of scientific inquiry itself. The pursuit of truth knows no borders. The laws of physics that govern the tidal heating of Europa are the same in Tokyo as they are in Paris. The chemical processes that might support life in a subsurface ocean obey the same principles whether they are studied in Mumbai or Rio de Janeiro. In uniting to explore Europa, we are celebrating this universal language of science, demonstrating that our shared curiosity and our common desire to understand our place in the cosmos are forces far more powerful than any terrestrial division. This collective endeavor stands as a testament to what we can achieve when we direct our resources and our intellect not toward earthly conflicts, but toward the peaceful, shared exploration of the heavens, reminding us that we are, first and foremost, a single crew on spaceship Earth, gazing out together at the boundless mysteries waiting to be solved. Beyond the raw science and breathtaking engineering, this grand quest to unlock Europa's secrets serves a purpose even deeper than discovery itself. It acts as a powerful beacon, illuminating the path for the next generation of explorers, thinkers, and dreamers. The story of a hidden ocean and the robots we build to find it possesses a unique magnetic quality that captures the imagination in a way few other scientific endeavors can. It's a narrative woven from equal parts mystery and adventure, a real-life epic that plays out on a cosmic stage, and it has an incredible power to spark a lifelong passion for science, technology, engineering, and mathematics in young minds across the globe. When a student learns about a moon where geysers blast water into space or a submarine might one day navigate a dark alien sea, they aren't just memorizing facts for a test. They are being invited into a story. They can picture themselves as the astrobiologist who deciphers the first signs of life in a data stream, or the engineer who designs the drill that melts through the ice, or the programmer who writes the AI that guides a lander to a safe touchdown. This isn't abstract, it's aspirational. It provides a tangible, thrilling goal that makes the sometimes challenging subjects of calculus, physics, and chemistry feel not like hurdles, but like essential tools for the greatest adventure humanity has ever known. Class projects transform from theoretical exercises into mission simulations, where building a model cryobot or calculating the energy required to heat water on a distant world makes the learning immediate, visceral, and deeply engaging. This inspirational effect creates a virtuous cycle that benefits everyone. The more the public, young and old, is captivated by these missions, the greater the collective support for the funding and political will required to make them a reality. Stunning images and groundbreaking discoveries from missions like Clipper and JUICE will dominate news cycles and social media feeds, reminding us all of what we can achieve when we choose to wonder, to explore, and to invest in our intellectual curiosity. This public engagement is the lifeblood of sustained exploration, ensuring that the mission after Clipper and the one after that continues to receive the backing it needs to move from the drawing board to the launch pad. Ultimately, the journey to Europa is about more than just finding answers to our oldest questions. It is about igniting the spark of curiosity that will lead to the questions we haven't even thought to ask yet. It is an investment in the future, a demonstration that our species is capable of looking beyond immediate challenges and dedicating ourselves to a grand generational project that offers no guaranteed return except knowledge itself. By reaching for this distant, icy world, we are not only searching for other life in the cosmos, we are nurturing the intellectual life on our own planet, inspiring the children who will one day stand on our shoulders and see even further into the magnificent, mysterious universe we all share. From a distant, cracked gleam in a telescope to a world that has captivated our collective imagination, Europa's journey in the human story is nothing short of breathtaking. We began by seeing a featureless dot, then a strange, line-scarred ice ball, and now we understand it as a dynamic ocean world, a place where the essential ingredients for life are swirling in the darkness, warmed by the gravitational embrace of a giant planet. We've pieced together this incredible narrative not with guesses, but with data, using robotic emissaries that traveled billions of miles to send back clues about hidden seas, erupting plumes, and a geologically young surface that hints at the profound activity below. Now we stand at the threshold of a new era, poised to turn hypothesis into knowledge. With the Europa Clipper and JUICE missions preparing for their journeys, we are no longer passive observers. We are active participants in a detective story 4.8 billion years in the making. These aren't just spacecraft, they are the most sophisticated habitability investigators ever built, armed with suites of instruments that will taste plume vapor, map the ice shell with radar, and scrutinize the surface in stunning detail. Within our lifetime, the data they return will allow us to finally answer the question that has haunted us for centuries: are we alone? The profound implication, the truly awe-inspiring thought as we conclude this exploration, is that the greatest discovery in human history may not be waiting in some distant galaxy, but right next door, orbiting a planet we can see with our own eyes on a clear night. Finding life, even in its most microscopic form, on that small, icy moon would irrevocably change everything. It would tell us that life is not a rare, fragile accident confined to our warm, rocky world, but a natural and common force in the cosmos. It would redefine our place in the universe, uniting humanity with a new planetary identity as we realize we are just one part of a vast living tapestry. The cracks on Europa's surface are more than just geological features. They are fissures in our understanding, and through them we are about to peer into a new reality.